33% of the new people that come to Mumbai are living in slums, where they don't have any access to, public services, sanitation, anything, something like that. And today, this is actually were statistics from 2010, so it's already outdated, but the total slum population in Mumbai is like the London population, right? And by 2050, Mumbai is expected to be the largest city in the world, and the slum population by then is going to be London plus New York City together, right? So it's kind of scary what we're going to face there, right? And unfortunately, what we have right now, what people driving the development of cities are doing right now. So unfortunately, the decisions that they make are still based on intuition. The best case is on limited data analysis. And although, as we heard also in previous lectures, there's a lot of effort on making data available and everything, the truth is there's still a lack of tools that support analysis and decision making in this domain. And the work that I'm going to present today is trying to bridge this gap, right? Using data visualization. So we already heard a little bit about data visualization. I'm going to maybe not tell you, give all the motivation that we already heard in the tutorial, but I'm going to talk a little bit about why should we care about data visualization, especially for maybe the students that are here. So this is the definition I like about data visualization, is that the computer-supported, the use of computer-supported interactive visual representations to amplify cognition. So the idea is that we want to help people to better think, learn, reflect about data using these visual representations, interactive visual representations that are supported by our tools in computer graphics and everything. So that's why we are talking about this in a computer science kind of environment, not like a design environment. Right? And I'm also very happy to say that I'm glad to be talking about visualization in a French-Brazil school, because France has a very strong tradition in data visualization, like starting from the early works on Charles Minard with the Napoleon map that we saw in the tutorial. Jacques Bertin is very famous with this work in the semiology of graphique, I think it's the pronunciation in French. And there is at least only one big group that I know in area, this group. I have many friends there, so they have a very big tradition, a long tradition in data visualization. So that's great too, that we are doing this in a French-Brazil school. So when we are doing data analysis, we are trying to come from data to insight. That's the V from value that we heard so many times here during the conference. And if you have done this before, you've noticed probably that this is not like an easy straight line. This is more like a bumpy road, where there's many things that you have to learn, like as we heard this morning, Professor Genoveva, like you have to know about data management, algorithms, statistics, machine learning, math, visualization, and all of this. And we have focused a lot on these things, and we have advanced a lot of this. But the reality, and also we heard about this in the tutorial, is that there is a bottleneck in this process, that there is someone that's needs to learn about data. Even if you use all of these things, there is someone that needs to look at the results and learn something from it. Right? And this is the bottleneck, and this is what visualization is about, to make this process scale for people, not for computers. Right? And just to give you an idea of the importance of the field, in 2012, the American government created this big data initiative that was meant to support research in the big data area, and like they outlined the research agenda and areas that they want to support. And data visualization in this 4-page document is mentioned 5 times as one of the important areas for development. So I've been talking like kind of abstractly about data visualization. I gave you a definition, but I want to show you one of the works that we've done. So let's just to warm up the conversation. So let's see if I can handle this with the mic and the mouse. And you guys probably know that if you give live demos, things might go wrong. So yeah, just bear with me if they do. So especially with old code, right? So old code is a problem. So let me try to do this. Yeah, that and the network. That's why I'm using my 4G, my cell phone, not a Wi-Fi. But let's see. So this is a system that we developed at New York University called TaxiVis. That was, as the name kind of suggests, was visualize taxi data in New York City. And what I'm showing you here are taxi pick-up and drop-off locations, like where people get a cab and leave the cab. This is kind of famous now. It was not as popular in 2013 when we did this work, or before that. So the city, you might ask why you only have pick-up and drop-off locations, not the path of the trip, right? So, and what we heard from the government there is that they don't have use for the data, so they simply don't have they didn't buy resources, they don't save the data, so they throw away, and they only keep starting in locations for, I don't know, for record purpose, right? So they, for each trip in New York City, they keep records of how many passengers, method payment, distance traveled, time, and locations of pick-up and drop-off of each trip of taxi. So what I'm showing you here is like 2 hours of trips in a morning in 2011. And what I'm going to show you is what can we kind of extract with this kind of data, right? So maybe as a start of the motivation, I was a student in New York City, and sometimes I would go out with my friends, and I would like, to get a cab to come back home. As a poor graduate student, I used to live in Brooklyn, not in Manhattan. That's super expensive. So I used to live around here, maybe. That's not a scary part, but it's like a poorer part than here in Manhattan. So when I'm here in Manhattan, where the fun is, and I want to go back home, I want to take a cab, and the driver says that I'm not taking you there, right? And the question is why this is the case, right? Why they want to do this? And we can try to answer this with data, right? We have all the data, what's happening there. So what I can do is that let me maybe get a small region of a portion of Manhattan where the fun is, like Midtown. And now I drew an area there, and I select all the trips that end there in that location. And maybe I want to select the trips maybe starting in Brooklyn, like that. So let me draw a region like that. And what this plot is showing here is like the number of trips that occur in each one of these regions, right? Maybe like 2 hours of data is not enough to do any sort of meaningful analysis, so let me try maybe to go for a full week of data. So let me go and query this data again. Once I query the data, of course I'm kind of, if I show you all the trips, it's kind of a lot of things, so I might hide and sample some so you can see in a better way. And since I got one full week, I might want to get more resolution on my plots. So I have now the graph of number of trips that happen in each one of these regions. The blue one is the one on the top, the orange one is the region on the bottom. And you see already that Brooklyn is not that much served by taxi service, right? Or was not served at that point. And if you look, for example, for the average price or fare per trip, you might say, okay, the average trip that comes to Brooklyn and starts in Brooklyn is more expensive. So it might say, okay, these guys want to go to Brooklyn, But if you compare, for example, for fare per mile driven, the blue one actually wins like sometimes twice or three times as much. So it might be the case that you can say, okay, there is no incentive for me to go to Brooklyn, why I'll compare to the oil or the gas that I'm spending, I'd rather stay in Manhattan, right? And like somebody with this type of even simple analysis can try to suggest some incentive that might make drivers go outside, for example, charge some extra for trips that go outside Manhattan, or instead actually what the New York City government did was they actually have separate classes of cabs now. These ones yellow cabs, they have now green cabs and so on that operate outside the Manhattan area. And you can do more, so for now I need two hands. Just a second. I removed the areas that don't serve me anymore, and now I want to say study the behavior of trips like close to the airport, like the main airport, JFK. Let me go to the number of trips again. There's another airport here close to in Queens called LaGuardia. This is the second main airport there, and you might want to compare, for example, with other transportation hubs. For example, the big train stations that are here, Penn Station that's around here, and maybe Grand Central Terminal that's around here. And now I want, maybe it's a mess, but I want to compare train versus airports, so I can kind of group these things, and now I have the green graph represents the trains, and I can kind of do the same with the airports, and now I can do a better analysis. So I have the behavior around trains and around the airports. I can also do something like, oops, it's not what I wanted to do. I wanted to do not what I wanted to do. To see what's the movement from one airport to the hubs, and now I can study this, right? So the nice thing about it is that it's very powerful to study queries with this data and with this kind of visual language. And you might say, okay, we looked at a week of data, but a week of data is not that much. We have, I think, here 3 years of worth of data, and I want to make some conclusions about it. So let me try to do something fun. So let's say where people go after they arrive at the airport. So let me do something like this. So I wanted to create a heat map to where people go after they arrive at the airport. So this is like the red area that you see here. And instead of using a week of data, I'm going to try to use maybe a year and a week. And then it's going to process something, and it comes back. Maybe I should have a plot over time for the entire year. And now I have the behavior for the entire year. This is the heat map. I'm going to normalize the heat map for the maximal density, and I get this small. Where am I? I'm going out these small locations. Any guesses? What are these? Where do people go after they arrive at the airport? So let's check. So there is a big spot around the Intercontinental, New York City. There is another big spot close to the Marriott and Times Square and so on. So you're right. So people go to the big hotels. So these are rich tourists. So looking at the plot at the bottom, what can you see that's interesting? What picks up your attention? So there is a big drop here that some of you have drew with your hands, so that calls your attention probably, right? So the nice thing about this is that you can check where it is. It's around August 27th, a Saturday in 2011, and you might want to, check what's happening there. You can kind of select this area and see what's the behavior even closer, and there is a snatch of time that there is no taxi activity. That's exactly when Irene hurricane hit New York City. And the nice thing is that even you didn't know about it probably, but now we found it just because we could look at the entire year of data, right? And the nice thing about it is that you can follow this, and as we heard before, moving people or moving cabs are nice sensors about cities, so we can use this to see how the city recovered from it. So that's a nice application of the paper of the system as well, right? So I hope this gives you an idea of the power of these systems, right? Even if we didn't know about the data, we could just explore in it and having the ability to, like, following this exploration process, we learn a lot about the city. And let's stand up again. Just to give you a general overview of the process, the user has some sort of task, interacts with the system that selects or creates new data with some sort of query. This data that's queried is mapped visually on the screen, and with visual inspection we learn something from the data, and the idea is that this process continues, right? This is interactive data visualization. And especially for the students here, I wanted to notice that every portion of this diagram has some sort of research going on to improve this process, right? And data visualization is an interdisciplinary area. The roots of it comes from human perception, human cognition. And I'm sorry that I didn't bring any examples, but I could play with you and make live experiments, and it would be fun. But I didn't do it. So we also have research in design and algorithms, so that these are really important. Data mining and data management are super important because, for example, in the system that I just showed you, we have 3 years worth of data. Each day is around 500,000 trips. So you do the math, it's a lot of things to manage, and you have to do all these calculations maybe in real time because you're usually selecting an area or a starting time that you didn't have it previously defined, right? And there is also like user interfaces for interaction. So if any of you is interested in data visualization, there's all the flavors there, depending on your interest. Sorry, I'm not used to using the mic. So just to give you an idea of my research, just a little bit of advertisements, since we are close and we need students for our graduate program. So if you want to come, my research involves designing systems to work with real-world applications. I actually started working with biologists and statisticians to study bird populations, and then I migrated to urban data analysis. So I started doing taxi and other sort of data analysis, and I'm going to talk later today. As I'm also going to talk about, there's also a big component of algorithms that support this type of exploration of data. And I'm also interested in how do you design visualization to communicate uncertainty or risk, right? And as I'm going to discuss, it's really also related to urban data analysis. So actually, I selected 4 of these to talk about. So the first one you kind of already saw. Just to give you, like, to tell you the story a little bit in more details. Why did we start looking at it? So we actually realized that the taxis are really important or good sensors of the city. Just by looking, for example, at this plot at the top, where they show the number of trips for 2 years of data, as we saw before, like we can get big weather events, just looking at the values here, but we can also find events that we didn't maybe expect, like the taxis strikes because of the gas prices, right? So we learned about this just because I was not from New York, so I just was looking at the data and okay, this happens also in New York. It's not only in Brazil that we have strikes, right? As I told you before, like we have around 500,000 trips a day, 13,000 at that point, 13,000 cabs, yellow cabs driving in the city. Now we have green cabs. We also have black cars and so on and so forth. So there is a lot of data to be analyzed there. It's kind of complex. We have not only locations and time, but we have other attributes that might be interested, like costs, tips. You can analyze, for example, which portions of the city gives tips, at what time, is there any correlation? Actually, we don't know. We didn't do this analysis in depth, but it would be interesting for anybody, if anybody wants to jump in and do it. And the thing that we noticed there is that the thing that I just showed you was not possible with the tools that the people at the government were using, right? They were used to go into a SQL terminal, type a query, and then get the result, load into another data software that could do the data analysis. But they couldn't do this kind of flow of analysis because they didn't have the right or proper tools, right? And what we did was to propose that system that was not on, which had the main contributions in the way that they interact with the system and the way that the query was done. So we had this, like in the paper, going into much detail of this visual language and what it can do. So there is a lot that you can do, especially you can translate SQL queries with like these polygons and selections and everything. And you can see the results in all these 3 views of the system. Just to give you food of thought, maybe some of the people are working on this right now. In 2012, there was this paper, like it was a kind of a position paper by one of the EU researchers and one of the Brazilian researchers. Also, it's like a French-Brazilian interaction there. That the current database technologies are not meant for, or are not designed for interactive data analysis. They were designed for in an age, on an era where you were satisfied with pressing a button and waiting overnight and getting the result back. Or maybe not overnight, but maybe a couple of hours or minutes and so on. And for visualization, we can't have minutes. We have to have at most seconds, right? And this was a problem, so we got, just as a matter of experiment, we got 2 off-shelf solutions, simple solutions. And just to give you an idea of the memory footprint, it was bad, like these are the indices that they build. And queries would take around like a couple seconds to 10 seconds for small queries. For big queries, it would take like half a minute or more. And I mean, we implemented like a data, I would say not data management, but data infrastructure that was kind of much faster. it's more specific, of course, but much faster. And the idea here is there's no actually scientific contribution, but it was an engineering experiment, right? So we did it, and then saw, okay, this what they said is true. We can't use what's off the shelf, right? One of the bad things in data visualization is that we still need somehow to keep reinventing ourselves, especially on the data handling part of it. This was true by then. It's not entirely true now because this started some of the research in this area, and there's so many contributions, but it was a nice verification of that assertion. Just to give you an idea what happened, we demoed the system to the people at the TLC, that's the Taxi and Limousine Commission in New York, and we got very positive results, and like they were very impressed with what they could do with a system like that. And they are actually, they were actually using the system. I don't know if they are using it right now anymore. But one of the nice things that such systems started, and I think it's something that we also have to start doing, is that by showing this, it kind of changed their culture because they wanted to start hiring programmers to do stuff like this. And it's something that they didn't have before, right? They had people that, could write a SQL query, but were not focusing on doing tools like this. And now that they have tools, they know that they can do this, it's much powerful, right? So they can hire people that can develop their own tools. And now we have jobs for the students that we graduate. That's good. So I'm gonna, so it's a good thing, and I think in Brazil we are still far from that reality, unfortunately. We don't have that many places, especially in government, for people that do this type of stuff, but I think showing this type of results are going to maybe open their eyes for the new possibilities, right? And the software, we have like the proof of concept code that's there in GitHub, and it has been used by a bunch of people now for analyzing bike data, energy consumption, property ownership, and everything. So it's being used by a lot of people. So this was the first project, and it started many follow-ups. One of them is that once you have that infrastructure and started looking at the data, you find things that are more interesting or more compelling or more, let's say, more in-depth analysis. So this work uses or tries to complement some visual exploration with algorithms. And let me tell you a little bit of motivation why we did that. So looking at the data, by chance I was looking at a particular moment in time and I found this picture. In this picture there was something that took my attention. So I don't know if you know a little bit about New York City, but in this, the roads that go this way are the big avenues, like 5th Avenue, 6th Avenue, and so on. And if you look at this picture, the 6th Avenue is kind of empty, right? And it was a surprise for me. I didn't know if it was like a bug in our code and everything. And I was going to check, and I Googled it, and it was happening. Bike tour, what they call the 5-borough bike tour, is like a marathon of bikes that started in what's called I forgot the name of the other borough. So that's the island that's in here. It goes to Manhattan, goes to Queens, Brooklyn, and then comes back. So it goes through all the 5 boroughs. Staten Island, yes, starts at Staten Island. The thing is, data like this, there are so many slices or so many ways that you can look at it, is that you might miss something like this, right? For example, this is a 2-hour interval in a particular day, but I have at that time 3 years worth of data, and I was missing this because I didn't know that was in there, right? So I started investigating and see, why did I miss this? So imagine that instead of looking for each hour or 2-hour interval, I was looking the data day by day, right? So if I were to compare that particular day where the bike tour happened and aggregate all the data for that day, and compare to other days of the week, this is a Sunday, so other Sundays, the Sunday right before and right after, I don't see a difference, right? If I were to look at the data through time and aggregate all the trips that happen in New York City, like the May 1st is the green line, and the bike tour happened like in this interval, I don't see a difference as well. There's no significant difference there. Right? So aggregation is good because it simplifies the data, but it hides patterns. That's the message here. So the question is, there's so many slides that you can look at, right? Where should you start? Is there something that you are missing, right? So the thing is, only data visualization, data exploration with visual tools is not enough, right? You might miss this stuff. You might learn a lot of things, but just visualization, it's powerful, but it's not enough. So we need something else. So we need to plug some computational power in this. So what we did was to design this kind of pipeline to do what we called event-guided exploration. So what we would do is that instead of looking or just looking at the data as in text, you would also look at events that happen in the data that could help you target portions of the data that you wouldn't look at before just because you're not lucky to find it, right? So the idea here is that we would start with the raw data, we would transform it to some sort of density data like the one that I showed you, right? We would aggregate with a reasonable resolution here. In our case, it was hour by hour. And then we would use some sort of tool to extract what we call these events. And the tool that we used was computational topology. And I'm not going to be technical here, but the idea that what this thing can do is that if this is the density that you designed from your data, for example, this would be the density of taxis in different locations of the city, right? What this thing can do is that find regions where the density is higher than its neighborhood or lower than its neighborhood. It would be local maximum, local minimum locations. And that was where the events that we wanted to find. So that's what we call the events. And the reason for that, if you imagine the roadblock that happened, it is like a minimum point of this density, right? It's a point where there's nothing happening there. And the nice thing about this is that it also gives you for free a tool for, if you look at this region, this small peak here, to simplify features that could come from noise. So that's one of the nice things about these tools. It comes for free for you. So once you've done this and you found for each time step these events, what we did is that we started to track these. So we wanted to see for how long these things happened, right? So how long did you have a block in that street or a street with very high activity? And as you expect, with any automatic algorithms, there's going to be false positives. So we came up with an interface that the users could explore these events and target the right ones, right? And this exploration comes as follows. So what we would do is that we would present this group of events to the user, sorted like by some sort of importance that comes from computational topology as well. So the higher, the most important ones. And what these circles would represent is that each event in different time steps that we found, when they are connected, is that because we track them over time, right? So here, for example, we have an event that happened twice in consecutive hours, for example, an event that happened twice in consecutive days, in consecutive weeks, and this one that happens every hour throughout the week, right? And we got these, the user would see this picture and the other picture that would allow him or her to analyze the range. What we call range is like the length of the event, like this duration. and the density, how many of these repetitions happen throughout in this interval. And just to give you what this picture would like, this data would look like here, the green one is dense, but it's short, so it comes here. The blue one is dense, but it's not short, it's long, it's up here. And the other ones follow the right locations, right? And the nice thing about this picture is that if you want to analyze hourly events, you do this, but you can change this resolution where you compute the density and range, not as hours, but as days. So, oh, sorry. And first, what we did is that you can look at this plot like, this cross is not there, but you can find like 4 distinct regions. This one contains the rare events that happens like in short periods. This one like frequent events, right? So you can change now by days. So if you change the resolution for days, the purple event that happened in 2 consecutive days, like the duration is 2 now, it's not 48 hours or 24 hours, whatever. So it comes here. If you change for weeks instead of days, now this one is, again, the range is 2, it's not all the hours anymore, right? So what can you do with this? So let's look at the graph of all the events that happened in October in New York City, right? So if we look at this plot, as I showed you, there are 4 regions. This is the rarest event. If you select it and you look at the map, this is exactly the Halloween parade, right? If you do it by day and you pick up one of the rarest events and you look at the most important one, you find that there are 2 parades that happen in consecutive days in the same area. Facts that we didn't know about and we now do, right? By looking at the data using this. Oops. And there are many more. I forgot to put my last slide that I wanted. So there are many more. One of the capabilities that we added there is that once you find one of these events, you can query for similar ones. And with querying for similar ones, you find the 5, for example, for the bike tour that I just showed you, we can find the Dominican Day Parade, the other bike tour that happens in a different year, the other Dominican Day Parade in the following year, and something that we didn't, it's not a parade. It was a protest in my city, in New York City, Gaza solidarity protest that happened to happen in the same area. But the thing is that it doesn't block entirely the street, so it's, but you can see by the density that's a minima there because it lowers the activity of taxi there. So again, we learned more about the data because we could extract this automatically, right? And again, this is a mix with interactive visualization and algorithms. So this is what we like to call visual analytics, not only visualization. So let me come back to this picture. And so what we did next was, okay, we have taxis, it's nice, but there's more movement than origin and destination. There's much more complexity there. And this is a picture that came from a data set that I think is the same one as in the tutorials, the GeoLife data set, right? So we are going to see more about it later, but what I wanted to show with this picture is that if I represent all the path that somebody's taking, naively, you don't see anything. You just see a mess, right? So the question is, how do you deal with this? So just to tell you about a little bit of what's happening here, because I'm going to reuse this color scheme. Blue is where a trajectory started, and I interpolated to orange where the trajectory ended, right? And so this was a theme of the work also that we did, I think in the same year, in which we tried to extract movement patterns in a way that would be easier to visualize. And then, so we wanted to solve the problem in that picture. So what did we do? We said, how can I solve this problem? How can I understand what's happening here? So we looked at what people have done. And people tried to go maybe 3D. And it can help you with something. So what they did here is that you have the path geographically, and the axis that's going outside the map is time. So it gives you a notion of what time is doing, but you lose entirely the geographical perspective, because you don't know exactly which point in the map represents this one or that one, for example. You can use aggregation again, but if you do, like, you pick all the roads, you count how many times people are passing through, and again, it gives you the idea of where the crowds are, but it doesn't give you the notion of where people started and ended, where people are going, right? And people are trying to do some sort of automatic analysis, but again, not focusing on visualization. So what we try to do here is, how can we improve the visualization with automatic algorithms again? So again, not trying to be technical, but to give you the intuition, what it is that we got this idea, what we call vector fields, and we try to use it as a matter of better visualizing the movement or trajectory data. So what did we do? So this is what we call a vector field. It's like, you imagine that there is an arrow in each position in space. And the idea there is that this already gives you a notion of movement, right? So this is, you can think of wind speed, or you can think of, you get a bucket full of water and you do this in the water, and the speed of the water is going to be something like this, right? And the nice thing about it is that if you place, let's say, if physics was nice for my example, if you place maybe a ping pong ball there, it would do this, right? If it was wind and there was like a dust particle, it would do something like this, right? And we are going to use this and think that our movement is something like dust in the wind, like very poetic, right? Our movement is like, we had wind that's like governing our movement, and we are going to use this model to, or this as a generative model for people's movement, right? So this is not important right now. So what we are going to do, like as a visual example, imagine that you have something like this, and our algorithm is going to figure out what would be the wind that generated the movement, and it would separate these guys in a nice way. The good thing about the wind metaphor is that if you place another ball down here, it can't intercept the other balls, the trajectory of the other ping pong ball, right? So that's the nice part about visualization, because we are trying to avoid as much as possible the crossing in some sense. We formulated this with some math that, again, I'm not going to get into much detail, but this, what we did is that we used this to generate like a formula that would be an energy function that we want to minimize. If you want details, I can give you later, but I think it's not that important right now. And what we can do is that we can optimize that formula using a simple algorithm, and that's an algorithm that follows the alternating optimization or approach. That's why we kind of, in a kind of a joke way, call it k-means. It's not exactly k-means, but it uses the same sort of process, right? But instead of working with points, it works with vector fields and trajectories. So let me show you what we can do with it. So as a validation data set or example, we created 2,000 trajectories with these two circular movements, and the idea is that you want to separate them, right? And the idea is that if you use different methods, you would mix these two patterns because they are close by here. So the idea is that using the vector fields, you can kind of get this general notion of movement. And the algorithm works as follows: you initialize it, and you extract the vector fields from these two portions of the trajectories, and you keep repeating it until the point that it converges and separates the circles in a nice way. Okay? And again, in the paper, I have many examples. I wanted to bring you to this one that is used in a coincident way in the tutorial as well. And you heard about it. That's the GeoLife data set from MSR, where they maybe they tracked. I think I can say that they tracked their employees, so you know where they went and everything. And what we did is that we cropped an area of the data set around the Microsoft Research Campus that's in Beijing. This is in China, in this area, right? We have around 12, almost 13,000 trajectories there. So we used our data set and we kind of say, okay, find me 4 movement patterns there. And it kind of cleans the visualization a little bit. So it gives you the movements in the rows. It's kind of a little bit convoluted the way that I'm showing you with the vector fields on top. But the nice thing about it is because it also gives you the idea of speed. Like the darker the arrows, the faster the movement is, right? And the idea is that these 2 different movement patterns kind of cleans where people arrive at Microsoft. So this is this orange portion here where people leave Microsoft and people using the train line to go north and south, right? And we said, okay, this is nice, but it's still a little convoluted. Let's use our algorithm again. And in one of the movement patterns, or in 2 of them, we saw this. For example, this is Microsoft campus, people coming to this location, and people in the other movement pattern are coming back from that location. And this is kind of hidden right here, but you wouldn't know because the picture was convoluted, right? And we didn't know China, but we went to Google Maps and we looked at it. This is an area with many noodle shops. Probably people go for lunch here and come back to work, right? You wouldn't know that just looking at this, right? It's tough, but now we do, okay? So again, this is another instance of, or another example where that visualization is helped by using some sort of computational intelligence there, right? And this algorithm is again gives you like an expressive way of finding these movement patterns. It's fast, in some sense highly parallelizable. It gives you the vector fields for free, so you get this notion of movement patterns there, and can be generalized by higher dimensions. Then one of the nice things that happened is that in 2015, people from, just getting a little bit outside urban data analysis, people from the what do you call it, medical community, got this algorithm and generalized to analyze brain fibers, and they said that this algorithm performs better than the ones that they have there, so they have used before. So it was a nice thing that they did. Okay. So coming back to urban data analysis, we have been looking at taxi movement and so on. But cities are complex environments. There's not only movement of people. There's so much going on, right? And in a project that we did in collaboration with architects, they wanted to use data about the city to decide where should they place new constructions or buildings, right? And much more than that, they wanted to see if I place a new building or a new construction in a particular location, how this would affect the city, right? So this is important because we want to make better decisions. So we want to see how my decision is going to affect the city. So in order to do this, we outlined what they want to do in 2 categories, right? 2 sorts of tasks. What they came up asking us was, they wanted to know what defines the character of a neighborhood, what's there, what's not, what's working and what's not working, so I can decide what I'm going to place in that particular location. And once I know that, and I know what the neighborhood needs, I wanted to know if I use this knowledge to build something new, how this would affect that neighborhood, right? And just for the terminology I use, call these data analysis tasks and these impact analysis tasks, right? And the first ones, like data analysis, we translated it as that what was needed was to be able to explore multiple data collections about the cities, right? So we wanted, if you wanted to decide, if you wanted to construct something in a particular location, you wanted to understand what's the transportation there, how is the population in that particular location is a violent neighborhood or not, and so on, right? If you want to build a hospital, probably you don't want to do it in a very noisy location or something like that, right? So you wanted to know all these things. And once you do this, what they wanted to do is to be able to replace a building, an existing building by a new one, and see how this would impact the city. And in this particular work, the impact was related to visibility. So this is a very important issue. It's not the only issue. For example, just imagine that we had this problem in Recife recently, where people wanted to build how do you call this, viaduto? Eu esqueci como chama viaduto. Like this pathway that goes above the, I forgot the name of it in English. Huh? It's not a highway, but this elevated street that there's another street below it and one goes on top. I forgot. But I forgot the name in English, sorry. But the nice thing, the bad thing is that it would block the view for the old churches in Olinda, right? So people don't like that, right? And you also imagine that, for example, if from your apartment you can see, I don't know, what would be the beach here in Natal, and then they wanted to put another building in front of it, and you're going to stop seeing the beach, you're not going to like it, right? And probably what's going to happen is that the cost of the value of your apartment is going to go down, right? Because the visibility is very related to price, right? And so they wanted to analyze that, and they defined these two measures that I'm going to come back later. And we wanted to see how we can do all of this interactively, as in the data in the TechCV's example. We wanted to explore more complex collections of data in the city, right? And we looked at what was out there and how they would support data analysis and impact analysis. And what we saw is that there were many data sets that were supposed to analyze a single system, that was supposed to analyze a single data set as it is. There is no evolution or no change in the city, right? Our TechCV is one of these, right? Where some try to go to multiple data sets, but again, as the city is no evolution, right? The architects that we worked with, we used to do impact analysis with geometric modeling software, but again, it's a standalone solution for impact analysis, not data analysis, right? And then there are software packages like ArcGIS that are kind of general, you can build on top of it, but the efficiency is not good, right? So what we did was to build a system that could have support this multiple data set analysis and also interactive impact analysis. So we built like some sort of GIS infrastructure that would allow you to see multiple types of how do you call data layers, and I'm going to show you the example, so I'm not going to focus on this, but you can see 2D and 3D layers in that particular system. You can do impact measures with sky exposure. For example, what you wanted to do is that you wanted to measure how much of the sky you can see in a particular location. This is important for example, by light exposure, there's the illumination, right? So that's important for the streets. And the important thing in big cities, I don't know if it's here in Brazil, in New York there are regulations for this, right? There are rules. You cannot build anything that you want. Right? There are rules that you have to follow to build new things. So what we wanted to do is that once you replace this white building by these dashed line ones, how much this would affect the visibility for the sky, right? And what we did is that we used computer graphics to do it. Like maybe since we are doing everything in computer graphics, why not? So we had the geometry of the buildings, we have the streets, we simply put a camera there, an artificial camera, look up and take a photo, right? But we do this for the entire city, right? If we do this for the entire city, we know the sky exposure everywhere, right? For visibility, what we did is that, given a landmark, we want to be able to measure how much a change would impact the view to that landmark. And what we did is that, imagine that my landmark of study now is the Freedom Tower. That is the one that replaced the World Trade Center. And if you wanted to build another building and measure the visibility to it, the problem is that you cannot. There is no single viewpoint like the one in the sky exposure that you want to take a picture from, right? But what we did is the simple observation that if you can see a building, the building can also see you. And we took pictures from the building instead of seeing from the other buildings. And then we measured the visibility from it. So we took, what we did is that we took many intervals in height and in angle. And we took many pictures and keep track of which one of the other buildings can you see, right? So just to give you an idea of how this works, this is a series of videos showing the architects working with this. So they would start by looking at the data layers that we have, in this case transportation, in the context of buildings, and see, for example, areas where the transportation is available or not. They can control the opacity of the building so they can see what's behind it. Once you have this, you can not only look at data layers in isolation, but you can look one in context of the other. So for this we used parallel coordinates. If you were in the tutorial yesterday, you heard about them, to represent the different data attributes that we looked, for example, crime, transportation, presence of restaurants, and etc. And you can select neighborhoods that would satisfy these filters, right? Once you select the neighborhood of interest, you do the same for buildings. For example, you can select buildings that have the lot that's the area of the lot that's available or it's constructed, that's close to crime, that's small noise, and so on. That would highlight the buildings here. And once you select buildings, what you can do is that you can replace them by new ones, that is colorful ones that are here, and you can select and replace them, right? And once you do this, you can study how much they impact the city by the sky exposure first. So it's we're gonna show the sky exposure on the streets and how this change impacted. So we're gonna compute it and show, for example, areas where it impacted negatively in red, positively in blue, and we select the landmark of interest and we study how it affects the visibility, where it increases and where it decreases, right? This change is actually negatively affected of all these areas. So basically, it's a bad change for all these people here, right? And the nice thing is that we got a very positive feedback from the architects. They were happy. They wanted to use this, and it was the first time that they could do this sort of analysis interactively. And also it was a nice thing that they wanted to show this in the meeting with the real clients, which was really good. Now they have this to show to them, right? The nice thing is, in the taxi-based case, once you have this type of infrastructure, it starts new types of research. And this was actually the point where I left NYU, New York University. So I stopped working in this project, unfortunately. But my colleagues keep going, and it generated works like studying shadows in cities, because it is also important as sky exposure. For example, if you change a building, how much of shadows are, or how the shadows behave. So, and this got a lot of attention, and this is actually in New York Times. So New York Times picked up what they did and put it there. There is somebody also working with wind movement inside the city now, again using the same infrastructure. And just as a summary, I hope I convinced you that it's an important problem, and there is a strong need for tools to support decision making in this domain. It's a source of interesting collaboration and interesting problems, and potential for real impact, even if it's just to change their culture and make them hire programmers, right? But this is also an important contribution. Just as some thoughts for the future, if I can have some, I see that a way to, for us to prepare for changes is a combination of visualization of data analysis and what I call the simulation, right? So this idea of I have to have a way to assess how my decisions are going to impact my environment. It's not just a matter of it's in my head and I have the intuition that this is going to be good, but I have to have a way, at least my models can be wrong, but it probably helps me if I'm wrong, or maybe it's what's the right analogy? Maybe it's more people thinking, right? So it's not just me, but me and the computer helping me to browse the space of solutions. And I also see that it's important for us to support not only experts to help cities to be smarter, but to support citizens to help them to make the city smarter, right? There is no good way, I don't think, at least from the cities that I know, to see what's happening there, to help government to make better decisions. Is everything is centralized, right? Everything is in the hands of a small group of people, and I think we have the capability of doing more. Not only watching what they are doing and how they are spending their money, but suggesting solutions, right? So I think that's it's a thing that we should focus as well. So how do we support people to understand what's happening? And it's more difficult than it sounds, right? Because I mean, my grandma is not going to understand my visualizations, right? But I want her to be able to give her experience, or maybe not my grandma, but my parents and so on, right? So communicating data to people that are not specializing in some sense, it's a tough problem, and is also a source of research, right? But we should try to focus in this direction, and for this there's all sorts of things involved: user interfaces, visual mappings, data management, and risk. We need all of this to build the tools that are going to guide us there, right? And I hope that I convince you that you should join us in this journey. So yeah, thank you.
Okay, let's open for some questions. Now we have microphone. Just raise your hand and make your question. Okay.
Thanks a lot for your talk and congratulations for your work. The question is, during your talk, you said that visualization is not enough. You need algorithm models and no, it's me, baby. So even if visualization is not enough in all these contexts, which is the big challenge of visualization for you?
Well, there are many of them. So one of the biggest ones that I see is how to make it scale, right? So you want to have algorithms, even if you have somehow to compute heat maps on large data sets, it's going to take some time. You don't want it to take time, right? How would you make it scale for data sets that are really big, right? If you wanted to visualize it, it's already a problem. If you wanted to put analysis on top of it, it's another problem, right? Analysis as we are doing right now. So this is one of the biggest challenge that I see. The other, there are many others. For example, we don't fully understand now how people understand pictures from the perception side, We don't fully understand how people understand animations, because one of the solutions that is supposed to help us with the big data comes from sampling. And what you do there is that you keep sampling growing data sets, and your visualization keeps evolving, right? Because you're getting more and more data to analyze. How these changes are going to affect what people understand from data, right? How you make decisions under uncertainty, basically. That's what's going on there. This is another big challenge. Right? So I think these two are already enough. There are many more, but I think in visualization nowadays, what I've been trying to do and what many other people are trying to do is that how do you make it scale? It's tough. And how do you understand how people perceive data? People that do scientific simulations are in a very bad shape right now, because if we have problems with these sorts of data, they have data sets that can't they even store, right? Because they are so large that they are doing what they call in situ analysis. What they do is that as they generate the data, they visualize what they can and throw everything away, because they cannot store it. But for us, we are trying to make the humble steps of making this scale, these sort of things scale.
Another question? Just raise your hand. If I have a question, which tools of these are available to the community to work with? And
so the first one is the text one. It's available, as I mentioned, is at GitHub. The last one that I showed, this 3D one, I don't think the people from NYU haven't opened it, so unfortunately. They have the code. I'm pretty sure that if you want to work with them in something, you can talk to them and see if they can give you the code. But as far as I know, they haven't opened it yet, unfortunately. But I think there is one reason for that. Of course, sometimes people have an infrastructure that they can produce a bunch of stuff, and it's not only that they want to keep it, but it's a bunch of work to make it deployable and easy to use to other people, because these are research prototypes. It's not like refined product, like commercial products, right? And these, I mean, if I want to go to the real world right now, not everything is beautiful when you're doing this type of work, right? And for example, we were doing this in Linux environments because we are kind of programmers. The architect uses Windows, right? And for me to make a package that would be easy for them to open, like to double click on a button and show this, it required me like a week of doing it's my PhD work, right? And I was like trying to compile something on Windows, and it took me a week. And it's kind of, okay, I don't want to do this, but it's hard, right? So I think that's one of the issues, right? Polish software and keep maintaining software is stuff. The thing is that we want to show that this is possible to do, but I'm pretty sure that they can open the code if there's a strong need for it.
You started with India, and my question is how I have the impression, of course, your examples are very consolidated, but they are related to a city that is well modeled. You have 3D models, you have a lot of information about it. What about cities where you have fewer information? How to get from this few information into such kind of solution?
Yeah. So one of the things that we try to do is to use as much open data as possible. That's one of the things. So if you have open data, we can do this. For example, pretty much all the buildings that you see here, there are from OpenStreetMaps. All those geometries there. So if you don't have OpenStreetMaps like completely consolidated here, you could maybe ask the community to complete it, and then you could use at least have not refined models but rough ones that you could maybe start analyzing. All of the data that we had, again, it's open, but it's a problem that, as you said, we need data in your talk, right? And it's important that we have this open data that we can work with. One of the tough problems here that we face, that's why one of the reasons I asked you to put the question in the morning is that for New York City alone, where we did this analysis, we had to do a lot of work to get the data from different sources, to clean it, process it, and integrate it, right? And this is a tough work. It's as much work as building the system somehow. Sometimes it's kind of, we spend so much time getting the data and cleaning it and trying to integrate it in a nice way, that I think we need standards, right? We need standards that, okay, if New York City is this way, New York, the open data in New York is not good in any way, but if all the data sets follow the same formats and everything, we could do the same in all the cities that make it available. But unfortunately, we can't. We don't have right now. But yeah, we need the data. So. Yes, I think so. So we don't have to keep reinventing ourselves in processing data and everything. We could reuse it, download automatically all the data sets from the different cities, and go from there. I think that would help us a lot.
Hello. First of all, I'd like to say that the presentation was very nice. My question is that the applications that you showed are very useful, very nice. I'd like to know if were they developed just for academic and scientific purpose, or are they used for making money or in a commercial way?
So we didn't make any money of it, if you're asking. Unfortunately, I wish I could have made money. But so the idea that usually happens is the following. So we, as academics, we get data and we spit out products that people could or could not use. So in the taxi example, I actually, like my advisor built the contact. I actually went to the taxi limousine commission office with like external hard drive and gave to them, and I waited for 2 hours for them to copy everything and bring it back, because it was not on the internet yet. Nowadays it's on the internet, so it's easy. Everything is easy right now. But I had to go there. And what we did is that we got the system and we gave them back the system, right? So that's what we did. In this one, it was with architects. It's a very big architectural firm, and since they are very big, they have an R&D department, right? Research and development department. With this, like in a company that had hundreds of people, they have like 5 people in R&D. And even to convince the big people there that R&D is important, it's tough, right? Because why they should support R&D? And what we gave them the system for free. This is not because they were helping in the design, right? And they had the idea that we could have a startup or something with that, but I mean it was not our focus. Our focus was on producing papers at that point. So that's what we did.
Okay, thank you. I asked that because I think that at the moment the big challenge is to extract the information about the data. At the moment the challenge is scientific, to extract the information. But I think that in the next moment, the following step, well, to convince that the information that are extracted from data can make money. No, because I think that at the moment, even the government and the private company are not, I think that they don't see how they can make money with the information that are shown.
So that's a good point. I didn't show you everything that we had, in the evaluation. And okay, since he mentioned that, I'm going to come back to you and say this is another challenge, right? One of the challenges is that how do you measure the impact of all of this that I showed? Because one of the emails that we got from the commissioner of the Tax and Limousine Commission was that it improved the efficiency of their workers, because the work that they would do in a couple of days, they do in like 30 minutes or so. So it saves them time, but it's hard to measure this in money, right? Money measures. But I would say that in the architects is the same, right? It would save them the time, and they couldn't do this sorts of analysis before. They can now show them this to the client, but I mean, there's no direct connection of this with money, right? There's no, I mean, this is not outputting money to you. This is outputting, giving you a tool that can help you to produce the money. And it's hard to measure that, unfortunately. So, but you're right. So we need to show this more to other people, this sort of work. I'm not saying my work, but all the work that are being presented, so we can convince other people to, you know, that we do need visualization for something, or do we need data analysis for something.
Wake up. So, when you guys were working on the taxi-viz research, have you considered using Tableau? And if so, why did you? Did not use it to plot or show the representations of the data?
So there are many things. So one of the things that I mentioned, I just showed there, because, for example, see, if you put your data in the conventional database, it doesn't work, right? And Tableau actually relies on databases to do the data analysis. So, I mean, if you're doing with them, you can't, right? So unless you build your data infrastructure again. And, I mean, Tableau is nice, but, I mean, we always have to reinvent. If I wanted to have my visual language implemented in Tableau, I don't have Tableau code to put it there. So I can't do all of this. And I mean, the nice thing about it, you mentioned Tableau. When we presented this work, after that we got an email from the Tableau guys that wanted to work with us with that. So right, because they wanted to have these sort of things in Tableau. And unfortunately, I mean, I don't know if they did or not, but we didn't work with them. But we got emails from them because they wanted to have something like this in Tableau. Because it's that. Now I'm going to point another big problem, right? There is generality, and there is expressiveness or power, right? The more general you go, the less powerful you can be, because you want to support everything, and you can't do much. You can't customize as much as you could. All of these solutions are kind of customized solutions for, like, especially the taxi is not this one, but this one is like a general 3D map infrastructure, but like with the visibility component, right? But there is this trade-off, right? And Tableau is very general and is kind of powerful, but it's not as powerful as tools that you can customize. So there's the other point. So yeah.
Another one. Nivan, you can tell a bit more about the tools and infrastructure use it to.
So all of this is custom built. So it's like, especially the last one is OpenGL, C++, and everything from scratch. So TaxiViz is C++, Qt, OpenGL. The other one that I didn't talk about is Qt and OpenGL, the what they call BirdViz, the bird population ones. So all of this is custom built. Yeah. So yeah, it takes. That's another problem. It takes a lot of time to build one of these. But once you have, you can do a bunch of stuff. Yeah.
Maybe we have time for another last question. Maybe in the audience there are people that, wow, I want to work with visualization, maybe undergraduate students or graduate students. So consider your experience, how to start, and which path they should follow, for example. Considering your experience, maybe the tools, what study first, what learn first?
I mean, if you wanted to use what people are using right now, and I think what people are going towards, I think everybody's moving to the web. Most of the people is moving to the web because they don't want to spend a week compiling C++ code to give to somebody else. I mean, pretty much everybody uses. I mean, there are two ways. So there's a lot of people using Python and Python notebooks to do stuff. So there's a lot of stuff going on there. In the tutorial, I think is a nice way to start. I think we already have a lot of slides with theory there. I think it's good to help with the perception and everything. But I think what most people use nowadays are D3 and JavaScript. I think this is the biggest software component that everybody is using, and people are already have built stuff on top of D3, right? But I think we have two things that we need to learn. Like, we as data visualization people, we are software developers at some point, but we are not only software developers. And I think the visualization education needs to go with data science somehow, right? Like AI, data management, and so on. Because I think if you know what to implement, you can Google it and implement it. But I think the challenge is to know how to implement it, right? What to implement. And this comes with some sort of maturity on know how you would, analyze data. So it's not simply like, okay, I know D3, I know that I can use the Google Maps API, and I'm going to put a bunch of dots on the map. Despite that, this is what I did most of my PhD, was to put dots on the map. But you need to know how, I spent 6, maybe 5 years putting dots on the map. So there is something to learn there, I guess. I think those two things go together. It's not only programming. Programming would be the first, but the foundations of data analysis needs to be there. Okay?
The last question.
As you can see, you learn a lot in New York. I want to know if you are working something now here in Brazil.
Working or teaching and everything. Yes, I am. I'm now in Pernambuco, so I'm not far from here. I'm 1 hour flight. Unfortunately, I'm the only visualization researcher in Pernambuco, and I guess, I don't know, there is a group in Ceará as well. So we have kind of, I think, 2 places in northeast of Brazil. And what can I say? Yes, so we are doing research there. We are still starting. Unfortunately, since this is a new area for us in Pernambuco, we don't have we don't attract as much students as I would want to have. But I've been there for a little over a year, so I am doing stuff there. So, but we need more students to come. So that's my bit of propaganda.
Thanks again, Professor Ivan Ferreira. We have some gifts for you. And we now have 30 minutes for coffee break, and after we wait you here. Thank you.
pessoal que trabalhou comigo, mas também eu já tinha saído. Eles fizeram um negócio que chama Urban Pulse, que era, eles queriam usar outros datasets, eles usaram, acho que foi Flickr, eu não sei se foi Flickr ou Foursquare, para comparar cidades, por exemplo. Áreas das cidades são parecidas, de uma cidade parecida com outra. Sim, eu já li um paper que fazia exatamente isso. E aí ele usou vários, exatamente esse, aí que eles usaram, saiu nas redes lá, nas coisas. E aí, cadê ele? Tem que me lembrar qual é. Aí eles usam Flickr, eu não sei se eles usam Foursquare, mas eu sei que eles usam Flickr, exatamente. Então a ideia é pegar dados de redes sociais, mas não texto, aqui não foi nada de texto, mas é usar, acho que, densidade de como as pessoas tiram foto, prestam foto para identificar as propriedades da cidade. Então, alguma coisa aí tem. Eu queria fazer uma época, porque tweets geolocalizados não são tantos e tem um acesso não é tão fácil. Mas uma coisa que eu queria fazer era, por exemplo, se tinha como inferir trajetórias de assuntos, por exemplo. Imagina que tem pessoas que estão falando de uma determinada coisa naquela área e você tem a trajetória que elas estão seguindo. Eu queria ver como os assuntos estão se movendo, no certo sentido. Isso eu pensei em fazer, mas a gente acabou não fazendo porque não tem os dados suficientes. Mas era, por exemplo, no Brasil. Era tipo, extrair dados e aí ver, por exemplo, o que é que está acontecendo com o que as pessoas estão tweetando ao longo do
2014 eu fiz algo parecido usando os dados das eleições. Eu tinha algumas tags, a Marina, Dilma, para ver de que forma o trabalho do Grenoble trabalhava na época. De que forma essas tags elas iam se comportando ao longo dos debates que tinham, entendeu? E geolocalizados.
Aí era isso que eu queria, assim, eu acho que, eu só não sei a aplicação disso, mas isso me pareceu uma coisa, assim, tal, não, digo para a minha ideia, não a sua, né? A sua tá legal porque tem um texto específico, mas assim, dá para fazer talvez alguma coisa que tivesse mais dados, eu não sei exatamente.
É porque quando estava no meu dataset, eu vi lá que tem dados de tipos, por exemplo. Isso. Eu lembro que tinha um dataset de táxis lá de New York, que ele dizia também que estava ocupado, não estava. Então eu fiquei pensando, será que não dá para extrair informações de tweets específicos? Tem gente que pega o Nuvem e bota uma opinião do cara sobre o cara.
Se você, eu acho que vai ser muito espaço, eu não tenho certeza, né? Tem que ver, por exemplo, se você consegue correlacionar que aquela pessoa naquele momento foi aquela pessoa que escreveu aquele tweet. Aí tem que pegar isso exatamente, ver se integração de dados que vai integração e talvez seja muito espaço realmente. Por exemplo, quantas pessoas que pegam táxi que realmente escrevem tweet na hora que estão dentro do táxi sobre o táxi ainda mais, né? Porque se ela escrever sobre alguma outra coisa, pode ser uma pessoa que está na rua falando daquela coisa, pode ser uma pessoa que realmente está dentro do táxi. Então é muito difícil você dizer assim. E é realmente aquela pessoa que tweetou, né? Porque você não tem que é o mesmo usuário. Mas difícil. Dá para fazer alguma coisa, só não sei com mínimo vai ser, né? Porque assim, eu não sei se vai ser realmente a pessoa que está dentro do táxi que está tweetando, né? Então, esse é um desafio. Mas seria interessantíssimo fazer.
E bota mais presente na frente da torre.
Valeu,
obrigado.
No sinal.
Opa.
Qualquer moneda da Paulista.
Eu guardei.
Eu acho que o mais da coisa é ganhar confiança na parte que a gente tem que entregar. Em termos de produtos concretos. Não apenas
o que acontece é que pra gente um evento é um lugar que quando a gente olha para aquela função da densidade, ele é um lugar ou de máximo, onde a função é máxima, uma região onde ela é maior do que o que está em volta dela, ou um lugar de mínimo, que é menor do que o que está em volta dela. E aí isso é um evento para a gente. Aí o que a gente faz é que a gente faz isso para todas as horas do ano, e aí a gente tenta ver se esse mínimo máximo se repete em outras horas. O que é que se repete? Se está no mesmo lugar e com a mesma intensidade. Se eles estão, a gente liga eles. E aí depois a gente explora a coleção dessas coisas ligadas. Se são muitas vezes que eles se repetem, etc. Mas o que caracteriza para nós é só ser máximo ou mínimo em cada fatia de dados. Não necessariamente se a quantidade. E esse é um ponto, é uma boa pergunta, é assim. A maneira com que você faz a densidade é você que diz. A densidade poderia ser a densidade de dinheiro, por exemplo. função qualquer que você pega dos seus dados. O que importa é que o que você seja interessado em máximo e mínimo daquela função. Porque aí tudo funciona, certo? Exatamente. Beleza. Nada. Okay. I need to return to this. Thank you very much. Very helpful. I forgot my.
para cantar. Es así de, como, ese es de acá, ¿no? De, qué cosa más linda, más
Probando, probando. 1, 2, 3.
Exclamation. Exclamation.
Which one? Wait. This one?
Yeah, yeah, yeah.
Autentificación. Continue. Let's mention passport. Connecting. Well, this one less blind but forward.
Okay, let's continue our programmation. Our second day. Now we will return to a tutorial we start yesterday with Javier Espinosa, professor. You are with.
Thank you.
Yes.
It's going to be difficult to put it into the plane. So. Okay, I'm having internet problems, but I put the slides in the Google Doc. So, if you want to have a look at the slides I presented yesterday, go and see by yourself. The idea for today is really to visit with you the exercise from yesterday. yesterday and to do some small things today. And at the end, I will present you some work that we are currently doing with my colleagues in Barcelona. And if, depending on the participation, we can discuss about other stuff. For instance, I have some material which I'm not going to present complete about geospatial visualization. So it's just to complete what you have heard recently. But before doing anything, how many of you arrived to run the exercise that you did? So, 1, 2, you do 1, so 2. What about the others? I assume that you had problems with the installation, right? Okay, too much. Yeah, because the proposal, my proposal is to do like a hackathon in the sense that we can. The idea is that we have the data. You don't know almost anything about the data, but well, you already have heard something about the data. But the idea is to explore the data. Now we have some tools for visualizing. You saw the heat maps using Google Maps. We have an infrastructure and a programming language for crushing some numbers. You, in principle, you are not familiar with the language and the programming model behind, so we can work together with that. So I ask you, for instance, how can we compute the distance for each trajectory? And you have to tell me, I don't know, we have to determine which is and then we do some kind of operation. So that the idea is to explore with you the data set and to see how to do it, right? So if you can run Docker with your machines, that's fine. I even think this is the better thing to do. Even yeah, and I can go with you guys for making the things running. I also have the help from Joao, who is a PhD student. He knows about the Spark. He has been working with Grenoble recently, so he can help. There are also 2 students at the back of the room who also know a little bit about the Spark. So the idea is to try to do the exercise. If you want to use your machines. Otherwise, I can do everything here, like in the classroom. I can present you some material just to give you the fundamentals. I don't know what do you think? Okay, so using the micro. Okay, well, so just a few comments. Niva is already gone, so such a shame. But you know, time, money is not everything, but still it helps. So, with respect to the question about the how much we can obtain from the visualization and this kind of stuff. Yesterday I present you a slide about the Big Data Value Association from the European Union. This is the report from 2017, so this is the report for this year. You have a lot of information inside, but one specific chapter, the document is not too big in size, you can read it, is the proposition about why the European Union has to invest time and energy into this area. And they give some numbers about the money, the quantities behind this, and the industries that are interested on that. The public institutions, also the private institutions, and so on. So if you are interested, you can have a look at it. it's interesting. You will also see the challenges for each of the steps in the value chain for obtaining value. The idea behind this report was to have a point of departure for starting doing some research in the European Union. So this is really interesting to read. Another thing that I would like to discuss about you. Placido asked about what you should learn today if you are if you are interested in visualization. Well, visualization in fact is a really nice domain which involves a lot of different expertises. So just to put you in context, this is one of our projects that we have with LAFMIA in France and Mexico and yes, it's the one that Genoveva showed you in the morning. So I'm showing this because I believe that the idea of the project is collecting data in real time, processing it, processing the data, and run some simulation, learning, and other stuff, and presenting it to the final user, but everything in real time, combining different data, real-time data, static data, historical data, and so on. The interesting part here is that you have people from computer science, also people from human interaction, the human interaction domain, and you also have, I don't know how to say, the people from control automatico. Yeah, automatic control. So, in fact, you need a lot of expertise to tackle these kind of projects. And, for instance, I remember at some point in the Barcelona Supercomputing Center, we have a good, close relationship with IBM. And they presented something similar to this in the sense that they were interested in combining big data architectures with high-performance computing architectures. The idea is that we want to visualize huge volumes of data, and each community has work by each at their own. And today, we need frameworks, operating system specialized for that, but also physical architectures. So, for instance, IBM and also Intel are defining new processors for tackling big data problems. So as you can see, if someone is interested in the visualization, there is a full stack where they can start participating. What you really need to know is you have to have a strong background in computer science. I mean, a really strong background on that. About this, well, just to show you one of the things that we are doing. So at some point, the idea, well, putting some marks on a map is not difficult, but well, the idea here is that we are receiving the information in real time. So we put the pins on the map, but at that time the idea was to show every these are taxis, every taxi on a three-dimensional space to do the visualization. And what happens is that this left side, well, there are different levels because at the right you see the car, well, maybe you see the car on the street, but the idea is that the user wants to move at different layers, maybe at the city or I don't know, the country level, and you have to adapt interactively the animation. So just to show you one of the latest things that we did, for instance, one of my colleagues sent me this today. This is just for you guys. So this Godzilla, in fact, is moving using real data points that were produced in Barcelona. So the buildings really correspond to a three-dimensional model of the city in Barcelona. Someone did this trajectory in the city. The data come from OpenStreetMaps, so we are playing the data. And for the time being, this is raw data. We have to process it we have to remove, there is a lot of noise, so we have to remove the data, to clean the data, to find the point of interest, and so on. That's for the people working in the database domain, like me. For those who work in the computer graphics domain, well, that the giant has to act like a normal citizen. Every time that the person moves to the, well, if the trajectory says that someone moved to the left, so this character has to also move in the same direction, like in a natural way. And this is just the beginning, because what we really want to do is to simulate millions of people in the city. So we are combining what those the people from computer graphics are doing with the expertise that we have treating the stream processing. So that's just a remark. Well, also before open the Jupyter, starting the environment. Oops, wait. I'm looking for. So the material I'm using is the one I prepared for a lecture on visualization. So because we were working with the smart cities, so we need to prepare the students for the visualization. And about geographical visualization, you know the principle. Someone gives you the maps of a city or a country, for instance Google Maps, for instance TomTom or other company. You have spatial data like the one we saw in the morning from Natal, and you combine both for making a map. Now, in this respect, you also know that there are some special data types that can be used for describing different types of events. For instance, you have points that can help you to represent restaurants. You have lines so that can be useful for representing the movement of a hurricane. Polygons for representing barrios. Here, how do you call them? Quarters? Yeah. So, and surface. And with these data types, those who are familiar with Postgres probably know that you have an algebra for querying these specific geometries. So you can, for instance, define whether a point is touching or inside a polygon, whether two lines intersect, and so on. Now, when doing maps, usually we are used to work with GPS coordinates, latitude, longitude locations. Now, the model behind this is a spherical model, but at this time, well, we are still using the two-dimensional space, even if it's très à la mode today of having the virtual reality. Well, when you flatten a sphere, you have a problem of representation. I don't know if this is clear enough, but let me show you some examples, because there are different ways of passing from a sphere to a two-dimensional space, and there are some consequences of choosing a representation. So this is like if you take an orange, you can tear it in many different ways. I'm going to skip that. The interesting part of this is that you have different map projections. The one that we use every day with Google or the Bing, for instance, is called Web Mercator. Have you heard about it? So, in fact, there are different projections, but the question, why I'm showing you this, because some projections, every projection has some kind of distortion. So you can see here, the bigger the circle, the bigger the distortion. So you have different projections, you have different distortions. So for instance, in this example, this looks like a continent because of the size, right? it's more bigger, it seems, than South America. But this is because of the projection. And this is exactly the same kind of projection that we use over internet. So if you really want to compare, I don't know, Pernambuco, the size of Pernambuco, to Rio Grande do Norte, it's not a good idea to use that one because you will be misleading by the projection. This is an example. So areas of the world that may be covered with ice for more than 90% in a specific year, using same data, two different projections. So with the Mercator, you can conclude that a lot of areas will be covered with ice, but in fact this is not the case, using a different projection. So this is all with respect. You have the slides, so you can look at this. Depending where in the world you are, depends the projection that you have, you can use. And this is just to show you how, from the artistic perspective, this was John Nelson at some point said, I want to plot all the hurricanes and tropical storms since 1985. And he used this perspective, which is not very interesting, but if you see it from the top, you have a different view, which is kind of nice to look, right? So this just to make you conscious about the different kind of projections. You just use the one that the tool provides you. So with respect to the special data, you have point data. You have heard. Basically, you have a map. You put points over the map. That's all, and you're happy. And you spend 5 years of your life just putting points. But these points are important because of the meaning. So this visualization, this is an example of a dot map with a lot of points. You can see the distribution in the population in the United States. So I'm going to skip this. I'm going to skip this because what I really want to show you, well, there is also, when you have line data, you can represent it using this kind of arrows, but this is not important. There are some really nice demos if you follow the links. But what I want to show you is this. Yeah, but I have to introduce this. Tomorrow you will work with choropleth maps. The basic principle of choropleth maps is that you are going to divide, for instance, a country, and you are going to assign a statistical variable to each region to observe statistical measurements. The problem with this kind of representation is that you will be misleading by the size of a region. So, for instance, here is the Hispanic population in the United States. So, greener the area, more Hispanic population is in the area. Yet, if you see in this, well, Texas, it seems that there is a lot of people, but if you see closer, you will see that, in fact, not all the area is Hispanic. So if you use different tools, no, there is one specific representation called cartograms. Basically, the size of a region is proportional to the data variable that you want to represent. So this is with the original map. The size of this polygon represents the number of people, for instance, voting for a specific candidate. But if you use this representation, you can see the where the people really vote. I'm going to show you the example. And this is creating this specific type of map is an NP-hard problem of optimizations. So this is why I started telling you there are many challenges. You need to have a very good background of computer science, and with that you can work with several people. These are multidisciplinary problems. So presidential results, for instance, here you can see who voted for who during the 2000 presidential election. So most of the time there is a lot of population in New York, you cannot appreciate how many people voted for, I don't remember who ran for these elections, or Florida. But if you see at the right, you can see how many people vote with respect to the other states. For instance, the same principle, but about religion. Well, I found this, I suppose it was a company from Barcelona. So just to show how many Catholics were in the world, according to some numbers, right? So the size of Brazil corresponds to the size of, the number of people in Brazil correspond to the size of the country, but you can see that Mexico, also United States. So you have to calculate the real size, and this is an optimization problem. I'm going to stop. Yeah, so before continuing, so as you have heard, for making your visualizations, you have either, you can use the package, some packages, but most of the time you use some tools. We are in the web era de la información, so people is using some JavaScript libraries, D3 for instance, for plotting into the browser. GeoJSON, we are going to use this. GeoJSON is a JSON format for representing polygons, lines, points, and polygons with spaces inside or not. There are also many sources for obtaining spatial data. OpenStreetMaps is the classical. You have heard many times OpenStreetMaps. Also, you have, if you are interested, for instance, in the frontiers of the of a country, natural earth data is an open data set that you can visit for obtaining the boundaries of a country. With respect to GeoJSON, as I said, this is a JSON-based format for representing geometries. So this is from Wikipedia. Basically, you are going to have collections of geometries represented by tuples type plus the name of the type and the coordinates. Coordinates are always arrays. So for instance, for representing a point, you have a JSON object. This object is of the type is point. The coordinates are just a two-value array. For representing lines, for representing movement, this is the one that we are going to use. You just put in an array all the coordinates represented as an array. And this is going to be put it into another object called features. So basically you have to build an object using this structure. The specification of your JSON is online, so you can check it if you are interested. So now let me start the environment. Okay, so with respect to, so this is the exercise that you saw yesterday. So I'm going to rerun it. So today you saw about Jupyter, so you know that you have the code, you put the code and you can execute it.
Do you have any question concerning the notion of the cluster in a Spark? Anything? No. No. Nothing.
Yeah. When you configure the was 2?
Yes. Thank you. Yes. Let me show you. Up. Wait. Docker compose. So this is the file. So the configuration I did is here. This is for Docker. When you run Docker compose up, Docker compose read this file and will create a container. Container is a virtual application. It's the instance of an image, of a Docker image. So the image in this case is one that I put online, that I created, with everything that you needed for the exercise. Even you can use, most of the material in this image can be used for the tutorial for tomorrow, I mean. But wait, anyway, when you start, when Docker Compose creates a Jupyter container, it will start the container with this instruction. pspark is the interpreter for Spark. And this line tells the address for connecting to the cluster. Since you are running a local cluster, this is the address is just local. But we recently, during a lecture, we create a cluster using the machines of the students. So in that case, we replace this with the IP of the machine acting as the master, and that's all. Here I'm telling that I want to provide only 2 cores to these clusters, but I can replace this with any number, and Docker and Spark will try to run the cluster with the maximum amount of memory and cluster in the environment. This is something that the administrator of the infrastructure has to define first. Yeah, but this is why you have only 2. Even when you are working, for instance, with stream processing, because as I said, Spark is an engine for doing computations over the clusters. So on top of the engine, you have different layers of well, they are APIs, but other runtime environments. So for dealing with streams, for instance, you need more than 2 cores for that. Why? Because there is 1 core just dedicated for listening connections, and other core working with the data. So if you just specify 1, you will receive the data, but nothing will be executed on them. Okay, so let's move. So I'm going to revisit the example. So the fact that the data resides in a distributed file system, does that make sense to you? So what else? The notion of this resilient distributed data set makes sense to you? For instance, you are familiar, I'm pretty sure you are familiar with Java. So what's the meaning of this instruction? Yes. So one interesting question, well, that was part of the exercise. In the data you have is here, yeah. You have latitude, longitude, altitude, days, blah, blah, but you don't have the user ID, right? So this is something we can do. I have to look for the example for copy pasting it. But basically, if you did like this, you can collect everything and visualize a heat map with all the data points from all the users, but you don't know anything about a specific user. well, yes, one if you run the, like this, because you can collect all the trajectories for user 10. Yes, specifically 10. So you can create your own script for running the rest of the things. So I'm going to skip this part because what happened? Wait, it didn't like it. What was the problem? So I run this, everything is okay. I run this, everything is okay. I run this. Yeah. I don't have the data. Anomality detections. Data now I have the data, I run. So question, why if I don't have the data I have a if there was no data I have the problem until this point and not before? If I loaded the data here with this instruction and then I moved there, why I had the problem until these points. Are you familiar with lazy evaluated expressions? So Spark is lazy evaluated. So the first time, every time you do an operation over an RDD, in fact you are just defining the graph of operations. At some point you have actions operation, like in this case collect, that will start the execution of everything. If you are database guys, so you know about the execution program, the execution plan. So basically every time you do an operation of RDD, it's like creating your own execution graph. So I'm going to skip this. So for instance, first and take 3 are examples of actions which triggers the execution of the query plan. In this case there are no really nothing to see. Let me skip this. Yeah. So RDD1 is the result of loading a specific text file. This one. Well, that one. I cannot double click. So just to be sure, do you remember? We can hear. This is functional. So you pass functions, and the result is something. For those who are interested in that, let me. I'm going to change this. So if you are not familiar, I'm sure that you are now familiar, but in case you are not, so basically this is what is happening. So I'm applying, this is returning a new data structure containing just a value, true or false, and you can see that the first 7 values, 6 values are false because these are the headers. So using this function is it's like this, that we are filtering the elements. We are applying the same functions to all the elements in the RDD, and since only the lines representing the header are returning false, at the end we finish with RDD containing just lines. So I'm moving forward to the parsing. Now, I just want to be sure that everybody understands this part. So we have lines, we have strings, but working with the strings is not it's strings with a specific format. So we have to parse them. We define a function, so we apply this function to every string representing a location, and the result in this case is what? So for each line in the RDD, I split the line. I define which are the dates, but this is the interesting part. Are you familiar with dictionaries? How many attributes are in this dictionary? 3. So we have latitude, longitude, and timestamp. We can. Well, I choose the dictionary. Do you have any idea why? I'm going to replace this. Let's suppose that I don't want this. I prefer rather to return a double. So this is the result. Now I'm returning a tuple. So I'm applying a function and I'm transforming a string into a tuple with 3 attributes, each attribute containing some information. When you print this, you really don't know what you are printing. So this is the reason why I choose to use dictionaries. The problem is that at some point I'm going to show you the example. I want to group by all the points that belong to a specific trajectory, and using the dictionary data structure in Python cannot be used for that. So you have to use other structures like the tuples. So, but what you have to keep in mind just is that return can return any data structure that you want, and you are going to produce a data collection using that data structure. So I move forward, so visualizing, creating the map. So this part, for those, I'm pretty sure that everybody is familiar with lambda expressions. So just a shorthand for the definition of a function. This function will return a tuple of 2 values, coordinate latitude and longitude. You can see an array of tuples here. Hop. I plot the map, and I'm going to continue. So yesterday I told you about that this was a train trajectory. And what is this? Making trajectory origin and destination. Yes. Wait a second. So this is the point. Yeah. So this part basically it tells you you have to find which is the first point in the trajectory. So the to-do was to complete the previous example to identify the destination of a trajectory. How do you find the initial and final point of a trajectory? So this is the code for obtaining the initial point. So you have a set of points. You know that all the points in the collection represent a trajectory. You have spatial coordinates plus time. How do you know the origin the origin of a trajectory and the destination. Yes. So, in fact, for answering this, you just have to check the API from Spark, because there are a lot of functions already coded. The interesting thing is that, as I said yesterday, this is coded on top of MapReduce of the MapReduce programming model. So in fact, if you want to compute this, you have, at the MapReduce way, you have to define a map function, a reduce function, just for obtaining this. But someone else did it for you. So let me check. So what we have an RTD containing all the information of a GPS log file. We filter the metadata, we parse the information. We obtain just the timestamps, and yeah, having the timestamps, I can use a function from Spark to obtain the min and max value. So this is the min max value. Now this is the interesting part. So I know the max value, but I need to check which element in the RDD contains that value. So, does that make sense to you? No? That's, I mean, well, the truth is that we have to plot it, and it has to make sense. Otherwise, I'm doing not n'importe quoi. So, using that information, let's see. Collect mark locations that. This is an interesting point. I need to union this. I have the origin, but look. Origin is an RDD. It's not a list, which means that the RDD resides in the cluster. But also I have, even if there is only one element, this is data structure lives in the cluster. We have another one, and we can mix them in the cluster and then collect them from the cluster. So I'm going to profit from that for using the union operation. So I'm going to define RDD3 equal origin plus origin RDD union distinct RDD in principle. This should have two elements. Here? This is RDD. Thanks. Yes. So, wait a second. So this is the final. So as I said, we have the execution plan. So we are making the union of two different RDDs, which happens to be in the same text file. So the environment is clever enough to just load once the file, and then it does the union. So now I can move to this place. Let's see. I'm improvising. Everything that can be grown is going to be grown. So RDD3, I need to produce tuples, latitude, longitude, collection, blah blah blah. So I close my fingers, and yeah. So we have the origin and the destination from that specific trajectory. Voila. So, any question? Simple. Piece of cake. Okay, but explore different GPS log files and try to discover points of interest, share your findings, try to use the union. Okay, well, the idea was that you explore with using different files. Let me see. I'm going to try to load two different users. No, three different users. So RDD1. So I want this trajectory. I want a second one. But yeah, just so that it makes sense. Three. So we have them. What do I have to do next? So I load them, and then what? Fit the map. I want to fit the metadata. So we have now the collection cleaned. Now what? So there is no header. We have parse. We can union. FTD1 dot union. FTD2 the result union. FTD3. No, because the first.
The origin and destination of each triangle.
No, I'm not completing the origin and destination. This is, I'm loading all the trajectory, three yes, I'm loading three different trajectories. I'm removing the header, I'm parsing, I'm just one data set. With that, in principle, if everything goes well, I can just replace this line I cross my fingers. Again. It printed something. Ah, yeah. Collect. Wait. Yeah. Ah. RDD. So I don't have the map. So the problem is I cannot see what is going on with yet. I think this is more interesting. So we are loading for 3 different files. So this is the execution. And in principle, these files reside in the distributed file system. So, but you can see the coordinate for accessing and making the computation. You also have information about the time for making the computation, the address, and the memory that was read by the system, the number of tasks executed, the cluster, and so on. So, and this is just that that takes a lot of time. So let's move to, I see. Yeah, the operation is taking time. And the problem is that it is trying to send everything to Google via my phone. So that was part of the experiment, to explore the limits. So let's move to the other example I prepared. So just let me copy this. The trajectories, but also you have a labels file. What happened is that the people working from Microsoft, they were volunteers for the experiment. So what they did is that for every trajectory, they put a label, a tag, saying I was walking, using a bicycle, a train, a car, whatever. Wait. Which one? This one, the one? No. Because the idea was just to give you we have to do this. How do you do it? But let me check. But I will put it on first execution.
basically the same. We have a file containing information independent. So every label file contains this information, the start time and the end time. So you have the initial point, the final point, plus the transportation log, bus, train, whatever. So if you have this information, what do you do? I mean, where is the tag? Where is the tag? Where? Where? In the level here. So basically we have to do the same thing. To load the file, remove the metadata, because we also have metadata, and to parse. In this case, this is very simple. So we load, we remove the line starting with the words, well, the phrase, the start line, and we print. Great. So, no metadata. But still, this has to be parsed. So this time, what I'm going to do is I'm not going to transform to a dictionary, but to a table. So this same principle. So we have all the labels in an RDT. We apply a function for transforming the lines into a useful data structure, the total, and now we have information. So we have the start time, the end time, plus the transportation. And what we can do with that? So we have files representing trajectories, multiple files. We have one file containing the beginning and the end of all the trajectories. So many files, one file. They should check. So maybe I'm going to this recycles. I'm recycling this part of the code from the previous example. So I'm loading a file containing trajectories, right? So we have in one RTG called log, we have a dictionary data structure containing latitude, longitude, and timestamp. On the other hand, we have a tuple containing the beginning and the end and the transportation of. You didn't take the database 101 course. Do you know join? Before joining, what do you do? The join, in fact, please explain the join operation. You have to cross it and filter it. Yeah, like the join does for Cartesian products, and then you filter by using a condition. Most of the time you use the AD join, which is just if you look for the similar attribute, and that's all. But you always do the cross product, which is an expensive operation, and this is why you always try to avoid the joining. So just let me start. So the idea is exactly the same. So the algorithm, the principle is that I want to compare every single point that we have in the trajectory with every beginning end pair of the labels. And if and only if the timestamp of the coordinate is inside the see the operation here. So let me just check. We have I load tables, I load one specific trajectory file, I feed clean everything, process, and then I apply the Cartesian product because already the operation already exists in the labels file with the log file of the RTD. And let's see the result. So this is the Cartesian product. So we have the result. Crossing two RTDs results in a new RTD composed of pairs of tuples AB, where A belongs to the first RTD and B belongs to the second one. So in this case, we have this is the tuple from the labels. This is going to have tuple of the parentheses, and here we have the collection, the position coordinate. That's all. So we have combined it. Now you can see that this is very ugly because we have a tuple. We have no way of naming it. So the following example simple states the Cartesian RTD, the result of the previous operation. I take the first element, and this, remember, these are binary tuples. So the 0 represents A, the 1 represents B. So again, we obtain what we had at the beginning. So this is the log line, and this is the label line, and this is the log line. Why I'm doing this? Just to prepare you for the filtering we have to filter. Cartesian, yeah. So we have combined everything with everything. So now we have to filter only those who belong to the trajectory. This is the if statement. I do the same thing. In principle, if we check this timestamp is inside this in the interval defined by this one and this one. I think this is the case. I see 49. So maybe this is the case. Yeah. And then we group by key. This is what I'm using top. So this is the key. When in the Spark, when you have an RTD and you want to group by, you have to specify which is the key. In this case, if the tuple is always the first attribute of the tuple. So I group, I wait, yeah. And this is interesting. So I only took the first element of the RTD, but remember, the result of this is all the tuples having the same key because we are grouping. So we have the start time, the end time, the transportation mode, and this, what does this represent? All the coordinates, yeah. For all the coordinates, yeah. So the result of this is a new structure of this tuple of two elements. So the key is a composed tuple, and the value is all the coordinates. So at this point, usually what you have to do is to verify if all the points in the data set that you have correspond to a trajectory. If you, well, I'm not going to show you because it is going to be complicated, but basically the collection that we have is not clean, it's not complete, and there are several things. Besides, I took a subset of the data set so that you can retrieve it easily. So, but well, that's the idea of using this.
I don't remember if this, I think this represents, let me check. Take one. Yes, this represents a taxi moving in Beijing. So, I'm going to zoom in. This is the line. This is a taxi. Yeah, that's a taxi. Cool. I'm flying taxi probably. I mean, there is no road here. Can you see? Oh, then. Well, let me check this. So it doesn't make sense. So that's the point of this exercise. It's just well, you have several tools, but you have the data. You can crush the numbers if you want. But at the end, once you visualize, you can detect things like, for instance, in this case, the coordinates do not correspond to something specific in the map. There is a reason. I'm going to switch. I'm using Google Maps as the maps provider because here you have the titles in English and French, but I'm going to use a second map. I hope this works. Using OpenStreetMaps. So this is the same trajectory. So this is exactly the same trajectory. I'm just changing the map provider. So, and you can see that this time it follows a highway. Yeah. So, and the reason, well, Google is not forbidden, but they are not anymore. Well, the
Right, some question? All right. Let's play.
Yes. Let me see. Let me start. Yeah. Let me check. These are the slides from a colleague. I remember he had some nice slides about that. I mean, there are many interesting stuff. For instance, this is for the people from the database, those who love spatial queries. There are a lot of material for that. But I'm looking. It's not here. Analyze maps, noise, clustering, spatial reasoning, not here. Visualize. Okay, I'm going to check for mine because the nice one I don't have. Where is it? This is not the one. No, this is not the one. Distance. Yeah. So I don't remember right now the name because there are different ways of computing the distance in the world. But basically, you take into account the radius of the Earth. You have the latitude and longitude, or universe of latitude and longitude. And you apply the formula. This is very simple math. So you, well, first you
right. Let's thank our colleague Javier. Thanks everyone. Now we finish the second day. We hope you have a good night of rest and sleep. And tomorrow we are here at 8:30 a.m. Have a good night. See you soon.
Thank you.